Hi, and welcome to a Calculus 1 video on continuity. This will be part 1 of probably a 3-part series walking you through continuity in your calculus course. So let's start with an overall fundamental idea of what continuity within a calculus course will be. So before we look at question number 1, let's actually define here what is continuity. And if you watched the pre-class video, or if you've seen any other videos on continuity, you probably have an idea that this is a 3-part definition. And basically what this definition says is that your left limit of your function is going to equal the right limit of your function, which is also going to equal your function's value. So there it is in words. Let me go ahead and write this using calculus. So here's my limit notation from the left. So the limit of any function, f of x, as x is approaching some a value, but again from the left, there's that negative there. Okay, it's going to equal the right limit. All right, so here's my right-hand limit, limit of f of x as x approaches a from the right. And then that will equal the function's value. So if it's f of x as x approaches a, we're saying that that should be equal to the f of a value, or that output at that a value. So it's a 3-part definition. So let's look at what this means for this first problem in our continuity notes here. So discuss the continuity of the function on the closed interval -1 to 4. So first and foremost, I'd like you to recognize this is a piecewise function that we are given. The first piece of my function is linear, just a line. And the second piece or graph is a line as well. So this yellow function is a line and this blue function is a line. So I could go ahead and graph these probably faster by hand than I can using a graphing calculator. So let's just take a look at what that is. I'll do the closed interval after I get the entire graph. So my piecewise functions are separating, or there is a break at x is approaching 0. So at x equals 0, I'm going to stop each graph. So I'm just going to draw the whole thing, and then when I'm done, I'll sort of erase the part that I don't want. So I want to draw the line 3 minus x. So that has a y-intercept of +3. So we'll say it's up here. And it has a slope of -1. So it's going to go through 3 over here. Okay, so let me draw that line for you. All right, so there's my line. Now, that line is only good when x is less than or equal to 0. So the only parts of that line that I'm going to actually want are the parts that are to the left of that y-axis. So let me erase the parts that I don't want. All right, so there. That's the only part that I want from that first part of the piecewise. So then for the second part of the piecewise, it also has a y-intercept, and that, by the way, does have a closed point, right, the yellow one, because it's or equal to 0. But on the blue one, it's going to be an open hole there. But I have a y-intercept of 3, so that would be the same point. It would be a hole, because at x equals 0, it's just greater than 0. It's not equal to, so that would be a hole, but I already have it filled in. And then I have a slope of +1/2. So it'll look something like so. And that will be the second part. Now the closed interval that I was given from the beginning, saying that I'm only going from x equals -1 to x equals 4, that means that I'm not going to have those arrows on the end. I'm going to look here at a closed window, -1 to 4, for example. So there are ends to these, okay? So if I only look in that window and I look graphically first, what I can see is that could you draw this from left to right, because we always look at things from left to right. So could I draw this from left to right without having to pick up my pencil? And that answer is yes, because I can start here at the left edge, I can draw. Where I exchange functions, where I go from function 1 to function 2, this is a closed-in point at 0, 3, and then I draw the rest. So I would say this is continuous over the entire interval -1 to 4. You could also say and argue that this is going to be continuous over your -infinity to infinity interval. That would be true as well, but we were only asked to discuss the continuity in the closed interval. Now, why did they give us the interval we did? Well, that's because this exchange between these two functions is what's really important. Where I stop being a part of function 1, or the yellow highlighted function, and I start drawing the second piece, or the blue function, that exchange between functions happens at x equals 0. Okay? So that's going to be where I'm concerned about the function's value equaling the left limit, equaling the right limit. And by the graph, I'm not really concerned anymore because I can see my left limit equals my right limit. They're both 3, which also equals that function value right there. But let's go ahead and just show it. What happens if we didn't have the graph or didn't want to draw the graph? Let me show you another way to look at this. All right, so if you just wanted to look at this numerically or algebraically, what you could say is this first curve, which I've always talked about as the yellow curve, this curve is going to end at 0, something, right? This is telling me where it's ending. X is good for all values less than or equal to 0. So this curve is going to end at 0, what? We'll substitute 0 in for x. That gives you a 3. All right, so then if I want to say where does this second function start, right? This function's going to start at 0 something. And what is that something? Well, substitute 0 in for x, and again I've been calling this the blue curve the whole time, so I'll continue with that trend. So if I put 0 in for x, 0 times a half is 0, plus 3 is 3. Now, it is important to note that because here's your or equal to, your function's value at 0 is 3. In other words, this one would be your function's value or your closed-in point, right? Because that's where you were equal to 0. So I can see from looking at this that my left limit, the yellow, is equal to the right limit, right? They both are 3, which is equal to my function's value, so I could say that I'm continuous there. So that should give us a good start. All right, so let's look at this next one here. Find, if any, the x values for which f is not continuous. Determine what type of discontinuity each point of discontinuity would be. So one thing that we have talked about prior to calculus is that, our denominator cannot be 0. And I hope from our limit discussion algebraically, we've looked at the idea, at least, of 0 over 0, and we will continue to talk about that throughout this calculus course. So let's really look at our denominator being 0, but let's really look at rewriting this as if it's a limit. So that's what we would do if it were a limit. We would have to rewrite this. So let's put this in a different form. By that I mean I'm going to factor this denominator. I made it decently easy to factor, hopefully. And I can see that I have a removable factor. Right, so this factor of x minus 1 is called removable. I can literally factor and remove it. It does leave behind a factor of 1. So then the question becomes, is this new function completely equivalent to the first function? And so if I wanted to color code them again, I could say, is this blue f exactly equal to the green? And that answer is no. If you look at the original function, this has 2 restrictions to the domain, because you are correct in saying that your denominator cannot be 0. So if I solve this using the 0 product property, hopefully you can easily see x cannot be -2 and x cannot be 1. But graphically, these are going to look different because that x equals 1 factor was the removable factor. So it's called removable discontinuity. And the removable discontinuity is going to turn into a hole graphically. Okay? Whereas the non-removable discontinuity turns into a vertical asymptote. So I have two pieces of discontinuity here, right? X cannot equal -2 and x cannot equal 1. Now it asks me for these answers in this positive way. It says find if any of the x values for which f is not continuous. So it is not continuous at x equals 2 and at x equals 1, and 2 is going to be the vertical asymptote and 1 is going to be the hole. So I can see that algebraically based on what factors I can remove versus not. And I can see it graphically. I'll show you here in a second. You'll see a big difference between a vertical asymptote and a hole in a graph. But I can also see it numerically. So let me show you that. So if I want to calculate f of 2, right, and f of 1, you're going to get very different numerical values. All right, so here's my original function, and it's actually not 2, it's -2 that I should be substituting in. So let's substitute in -2. Sorry about that. I'm going to get a -3 over -2 is 0. And if I substitute in a 1, I'm going to get 1 minus 1 is 0 over 1 plus 1, 2 minus 2, 0. So I can see this numerically because if I get something like -3 over 0, 4 over 0, 7 over 0, 9.8 over 0, some non-zero number divided by 0 that's undefined, I will see that as a vertical asymptote every time. If I get 0 over 0, remember when we were calculating with our limits and trying to figure out our limits algebraically here, that cued me in that I had some algebra that I could do. That's because it was probably removable discontinuity and a hole. Okay? So that might help us as well because we can always check our work numerically. So just in case our factors don't work or something like that. Let's look at the graph now of this function so we can see and double check that our continuity types are correct. All right, so it's important to note that when you type in the function, I'm going to make sure I type in the original function. Again, if I've made an error in factoring or something like that, I don't want it to show up now, right? And I can go ahead and just look at the graph in standard window, that's fine. And what I'll see is that it appears that at x equals -2, right, that I do have this vertical asymptote here. And then I can't see the hole at x equals 1 right now. It's not really showing me that jump or that point of discontinuity. But if I go ahead and say second calculate or second trace, gives you your calculate menu, a value at x equals 1, I can see that my y value here is blank, and that's because that is a hole. Depending on what your window looks like, you may actually see a jump at x equals 1, but I can just verify it quickly this way as well. Thanks for watching, and I hope you found this video on continuity, or the beginnings of continuity anyway, helpful. There will be more videos to follow. Thanks.